Okay, I'm going to go ahead and get started. So a couple of quick announcements. Remember that this Wednesday, what is that, the 29th? There's no class. It's a holiday for you, but I believe if you have any classes that meet like after 5, they do meet. So anything you have in the morning, though, or before 5 o'clock, you should have the day off. So we won't be meeting. So this is our only meeting for the week. So let's get to work. We have a lot to still try and get through. I did ask you to do 2 problems as a quiz to be picked up in class at the beginning of class. So if you could please turn those in. Just kind of get yours at each table, group them up, and then kind of pass them all to this table. I will also let you know that this morning my daughter wasn't feeling well. I don't know what was wrong with her, but she had a sore throat or something. And anyway, I have my phone on very quiet just in case the school calls. I just want to not, be able to hear it. So if that happens, I'll just take it outside real quick. Okay, anybody else want to turn in their quiz? I have your unit circle quiz from last time. I did post the grade in Canvas. I will hand those back at the end of class. And just remember I had said just maybe double check those to make sure that whoever graded yours didn't make any errors. And make sure you turn in your quiz if you're just coming in, if you have it. All right, would you all like me to go over the cosine one for the quiz? Yes? Anybody else? Okay, you have it on there? Okay, thank you. So yes, you would like to see 3 cosine 4x of 4x? Yes? Okay, so you were asked to graph, did I say y equals? Yeah, y equals 3 cosine 4x. Now the main reason I'm doing this is to try and get us thinking about this again. I know we had a long weekend, so today we're going to come up with a final way of graphing sine and cosine, a final method, and then we're going to move on to graphing the other trig functions, and we'll see how far we can get. So the basic idea was to first find the amplitude, right? So what is the amplitude of this particular trig function? It's 3, right? It's the number in front of the cosine or the number out in front of the sine if it were sine. So sine and cosine are done the exact same way, the way we graph them, okay, the method. So we find the amplitude. The next thing was to try and find the period, right? Or I should say, yeah, period. Now, what did I tell you to do here? 2 pi over b, right? 2 pi over b was the way we did it. And that will work for all the sine and cosine functions where what's inside, which is, I'm going to use some language here you may not have heard before. The thing that's inside the cosine or the thing that's inside the sine is called its argument. All right? So if the argument is just a number times x, like in this case 4 times x, if that's the case, then you can just say, okay, 2 pi over b, right? And b is this number out here, right? But as we move on today, you're going to see that what's in here, the argument, is not just going to be a number times number times x. It could be like 4x minus pi or something like that. In that case, we're going to have to do something slightly different. So I think what I'd like to do now is kind of introduce you to this idea. It's not much different than what we did before, but there is something different. So we said just take 2 pi and divide by b. That's what we said, right? Instead, what I'd like for you to do is this. Set the argument, which in this particular problem is what? 4x. Okay, set that argument equal to 2 things, 0, and then after that, 2 pi. That's what we're going to do for the rest of the class. Every time we go and try and find this period thing, we're going to do these 2 things. So let's take the argument, which is 4x. Let's set it equal to 0. And then a separate equation, let's take the 4x and set it equal to 2 pi. Do you all follow that? Now, the question might be, why are we doing this, right? Why are we setting it equal to 0 and 2 pi? Well, that goes back to the whole idea of your traditional, this is cosine, right? Here's our cosine curve. Here's our cosine curve, right? That's what cosine looks like. Are we all right with that? Starts out at 0, it's up at 1, and then at 2 pi, it's back up at 1. It does this dip down and comes back up, right? We know that at 0 and 2 pi, at the 2 endpoints, that our cosine curve is up at 1, right? We know that. So what we're doing by setting the argument equal to 0 and 2 pi is we're trying to figure out where these two peaks are. Once we figure out where the peaks are, then we can just come in and fill in the rest. Does that make sense? All right, so that's what we're going to do. Just trying to motivate why we're doing it. So on the first equation, if you're solving for x here, you divide both sides by 4, and 0 divided by 4, right, would just give you 0. Now on the other side, what do you have? Isn't that 2 pi divided by 4? Isn't that the same as saying 2 pi over b? Wasn't that the same exact thing? Yes? So we're actually doing that here, but this is way more powerful than what we did before, just saying 2 pi over b, because we're going to actually get both endpoints of the cosine curve. So divide by 4, 2 pi over 4, you reduce this. This is just pi over, what, 2? Okay? So what I know is that for this cosine curve, my 2 endpoints are going to occur at 0 and pi over 2. With me? Yay, yay? Okay, now the next thing that we talked about was looking at that interval on a number line and then cutting it into 4 equal sections. So what I would do now is I would go to a graph. Here's my x-axis. Here's my y-axis. I'm going to go to 0 and pi over 2. And I'm not going to put points, right? Not yet. I'm just going to label these on the x-axis. 0 is at the origin, here's 0. And then pi over 2, I'm going to put here. Now, I'm intentionally leaving some room to the right. Why am I leaving some room to the right? I mean, like, why didn't I put pi over 2 out here instead? Because, yeah, this would only be one period. I asked for one period and then one in each direction after that, right? So get an initial drawing and then go each way one time. So that's why I'm giving myself some room. If you're not happy with that and you'd like to extend your x-axis out further, you could. And then maybe we call this pi over 2. Either way, just allow yourself room. Any questions? Okay, now what we need to do is cut this into 4 equal subintervals. So how do we find the one in here? Well, we could just look, right? But I said, how do you do it? Anytime you have 2 numbers, you want to find the one between them? You average them, right? You add them up and divide by 2. So if I add these 2 together, 0 and pi over 2, 0 plus pi over 2 is just pi over 2. And then take that number and divide it by 2. So we would take that, divide by 2, take that, divide by 2. So you're cutting pi over 2 in half, which means you get pi over 4. Yes? So that would be here. And then what you do is you try and find these 2 And to do those, you go halfway between here and here, right? So same thing, you're going to add what two numbers? 0 and pi over 4. So add those together, you get pi over 4. Divide by 2, you get pi over, what's pi over 4 divided by 2? Pi over 8. So pi over 8 there. How about the one right in here? I'll show the work on that one. I'm doing pi over 4 plus pi over 2. I'm dividing that whole thing by 2. So how am I going to add these two together? Common denominator. So I need to get 4s on both of these, so I need to multiply top and bottom of that pi over 2 by 2. So I'm multiplying 2 on top and bottom here. Let me bring this down here. I'm kind of out of room up there. I have pi over 4 plus 2 pi over 4 all over 2. Now that I have the same denominator, I can say that the top is actually pi over 4 plus 2 pi over 4 is how many pi over 4? 3 pi over 4. And then I divide that whole thing by 2. So I get 3 pi over 8. Is that all right, everyone? Okay. You answered. Thank you. So I have 3 pi over 8. Now, we also talked about last time that if you knew this one, right, you could just count like this is pi over 8, this is 2 pi over 8, this is 3 pi over 8, this is 4 pi over 8, right, if you reduce the fractions. That's fine until later today when we actually shift this thing and move it, then it's not going to be as easy to count. So this whole idea of taking the average, to me, is the technique that will work all the time, so get used to it. All right, so now we know that this looks like a cosine curve, but what we need to do is figure out where the points are. Right now we think that the amplitude being 3, was it 3? Yeah. The amplitude being 3, we feel pretty confident that it's probably going to look like this. Now don't draw this yet. We think that the first point's going to be up here, the last point's going to be up here, right? For cosine. That's this point up here, and then this point up here. We think halfway through it's going to be down here, right? And then at the quarter points, you understand what I mean by the quarter point? Like a fourth of the way through it's here, 3/4 of the way through it's here. So we would probably feel good about this being here, 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 like that, right? And then we come through and draw it. Yes? Wait, from here? Because it's cosine. Just because it's cosine, yep. The difference between sine and cosine being, this is cosine. Cosine, the normal cosine function always starts at 1, drops down, comes back up, versus sine, I'll put sine there next to it. Sine starts at 0, goes up, comes down, goes back to 0. But it really, you still, even if you have some confusion with that, you can still graph this regardless of knowing whether or not it started at top or at 0. Because this is what we think it's going to be, but the actual technique of doing this is to not plot these points. It's to actually take these 1, 2, 3, 4, 5 values and plug them into the original function. Once you do that, you're guaranteed that your picture's right. Now that's tedious work, right? Plugging these in. But I'm going to plug in the first few and then see what we get. All right, so step 4 here is to plug in the 5 points. Plug in 5 points. All right, so when I say plug them in, I mean plug them into the original function. So let me start with 0. When I plug in 0 to the original curve, right, I get y equals 3 times cosine of, it was 4 times, we're plugging in 0, so get that, right? What's 4 times 0? 0, so 3 cosine of 0. And now we go back to the unit circle. But what is cosine of 0? So on the unit circle, cosine is which coordinate? X coordinate. I'm looking at the X coordinate. I'm looking at an angle of 0, right? So I'm going out to my unit circle. I'm going out angle 0, going out there, going to the X coordinate, which is what? 1, right? the x-coordinate would be 1. So I get a 1 there for cosine of 0. So 3 times 1 is 3. So I was right. I had a feeling that at 0 I was going to be up there at 3, right? And that's where I am. Bless you. This is pretty much all you need. You could actually graph the rest of it without doing any other points if you truly felt comfortable with cosine, because you know it starts up there. You know it's going to have to come down. It's going to have to go back up and end up there at the end. But let's just get that last. I'm going to do pi over 2 now, the other endpoint. If I plug in pi over 2, look how this works. Here's 4, here's pi over 2 next to it. When I multiply 4 times pi over 2, this 4 goes across the top, doesn't it? And it's really like 4 pi over 2. What's 4 pi divided by 2? 2 pi. So now again, you're asking yourself the same question. Cosine is the x-coordinate. Go to an angle of 2 pi. So here's 0, right? Come around. This is pi is 180, and then come back around. That's 2 pi. So where are you? Back at 1, right? The x-coordinate is 1. So that's also going to be 3 times 1, which is 3. So up here, we're there. Okay? I'll do one more point. I'm going to do the one right in the middle, pi over 4. I want you to see how this part of it works to make sure you're okay with that. I'm going to squeeze it in here. This is 3 cosine of 4 times pi over 4. Okay, what happens when I do 4 times pi over 4? What do I get? Right there. The 4s are going to do what? Cancel out, right? This 4 is on top, this 4 is on bottom. So they cancel, you just have pi. So what's 3 cosine pi? So when you go and look at cosine of pi, you're saying angle is pi. Go to the x-coordinate. What's the x-coordinate when your angle is pi? -1. So this turns out to be 3 times -1, which of course is -3. Right? So at pi over 4, I come down, I plot a point, -3. Then I can draw. I know, because it's cosine, that at the quarter mark and the 3/4 mark, it's going to be 0. That's just something you have to know about the cosine. The ends, it's at its peak. The quarter and 3/4 marks is at 0, and then at the middle point, it's down on the bottom. So now I'm going to draw this. And when I draw it, remember I talked a little bit about the smiles and the frowns type thing, not to draw straight lines here. So I'm going to go from this first top left point. I'm going to frown down here, and then I'm going to smile. I'm going to continue to smile, and then I'm going to frown like that. Does that make sense when I say that? That should be your cosine curve. That's one period of this particular cosine curve. Now I'm supposed to go in each direction, right? I'm supposed to go one period in each direction. That's what I asked for on the take-home. So I know that the period of this thing is the distance between here and here, right? Which for this problem is pi over 2. So I need to add another full period, a pi over 2 over here, right? To actually get another period, yes. Oh, did I not say 2 on this one, in each direction? Okay, that's fine. If you just did 1, I'll be happy with that. But let me show you, just so you have it. The next period would end where? Where would it end? At pi, right? You're taking this and you're doubling it. 2 times this, right, is going to be pi. And then you would have to come in and cut that in half, and then cut that in quarter marks, find those values, and redraw. So you know it would go through here, down here, here, up here, and then you frown, you smile, and you frown, like that. And then where would it be over here on this side? If this was from here to here was pi over 2, then going this direction would be what? Negative pi over 2, because I'm going in the negative direction. So this would be marked off at negative pi over 2. Then I'd have to find the halfway point, cut those in half, and do the same thing but draw it backwards. And you would get the same results. I'm not showing that work, okay? You would have to do that. And please understand, I would not expect that you find all these points and plug them in. I would expect that you actually find them, though. What are the values? But you don't have to plug them in because you know already this first period kind of sets up exactly what this function is going to look like in both directions. It just keeps repeating itself. Y'all with me? Okay, so that was the homework. I hope that those two problems at least kind of got your brain going on it. Today what we're going to focus on is we said already if we had a sine function like this that we could change the height by changing the amplitude, right? And we also said that we could change the period, which would change its frequency, right? Like how often they're happening. But I would like us to also address the possibility that, let me pull that, change the period, bring it back. Okay, see, so this period is shorter than the original one. But what about what we call a phase shift? Phase shift is basically a left and right shift. You see me moving the graph, moving it left and right here? Y'all see that? Look, y'all see me dragging this little thing across on this right here? You see that? When I go right, where does the graph go? Left. And when I go left, where does it go? Right. That's the way what we call horizontal shifts work in math. I don't know if you remember from college algebra when you were doing shifting of functions, that when you added a number inside the function, it moved it to the left, and when you subtracted a number inside the function, it moved it to the right. Y'all remember that? Yeah. And then what about to make it go up and down? There you added a number on the outside of the function, and that works the way you think. Look, if I take a number and I add it, watch what happens. I move the whole graph up, or if I subtract a number, it comes down. So our goal today is to try and be able to graph something like this, right? Here's the original sine curve, and what we're going to do is we're going to change its amplitude, we're going to change its period, we're going to do a phase shift, and we're going to move the whole thing. So how do we do all that, right? That's a lot to have to wrap your head around. So let's start out with an example. I would like for us to, what example am I on here? This would be example 3. I think I did 2 last class. Okay, I only did 1, so this will be example 2. Let's sketch -3 sine of 2x plus pi over 4. All right, y equals, sorry. I'll put the y equals on the other side. All right, so we have a pretty big mess here, don't we? The way I'd like for you to just kind of visualize this right now is we have like an A in front of our sine. That was like our amplitude, right? We have a B in front of our x. That B somehow controls the period, doesn't it? Then we have plus this new number, C. We never had that before. That number controls your phase shift. That's going to be your left and right shift. For this example, I've decided to not move it up or down yet. I'll do that on the next example. I just kind of, want to work our way into this. So the only thing that's changed in this problem from the one before is we have a phase shift. You'll see it? Y'all understand where the phase shift is? Okay. So this is going to move our graph by pi over 4. Which direction? Left or right? Because we're adding the number, and that pi over 4 is inside the function, right? It's in the argument. That's going to be a shift to the left. It's opposite of what we think. But the thing is, we don't need to worry about all that. All we have to do is still find those 2 endpoints get our 5 points, plug them in, we're done. Okay, that's all we still have to do. Now, I will identify in the first part the amplitude. What's our amplitude? -3. So remember, though, amplitude is always the absolute value of that number. So the amplitude would be 3. The amplitude just tells us like how high one of those arcs of our sine function are. All right, so let's get the period. Now, we've called this period, right? But truly what we're doing, just so we're all clear on it, we're actually finding what are called, endpoints. Aren't we? We're finding out those 2 endpoints of our period. We're not actually finding the period, the length. We're just figuring out where those 2 things are. So what did I say we do to figure out where our endpoints are for our period? Set it, what's it? The argument, which for us is 2x plus pi over 4, the whole thing. You set that equal to first what? 0, and then 2x plus pi over 4, you set that equal to what? 2 pi. Always, all right? That's the good news. For sine and cosine, it's always going to be 0. It's always going to be 2 pi, the two equations that you set up. Now, the argument's going to be different in every problem, but that definitely has to be the same. All right, so that is good news. These won't change. All right, let's try and solve this first equation. I'm trying to solve for x. So when we have, this is a linear equation in x, we're going to isolate the x term. So we're going to move this whole thing to the other side by subtracting it. So we get 2x equals negative pi over 4. Then what? Divide by 2, right? When we divide by 2, what's been happening anytime we've divided a fraction by 2? What's really happening? You're just doubling the denominator, aren't you? So this is going to become x equals negative pi over 8. Good. All right, so that's one of the endpoints of my sine curve. Now I have to do the other one. Now, this one's a little bit more involved because I have 2 pi over there. I'm subtracting pi over 4, right? I subtracted pi over 4 on both sides. In order to actually subtract these, what are you going to have to do? Get a common denominator, right? So that 2 pi is really like a 2 pi over 1. So it becomes, I have to multiply top and bottom there by what? Right, top and bottom of this fraction by 4. So we're going to get 8 pi over 4 minus pi over 4, which is how many pi over 4s? 7 of them, right? 7 pi over 4s. Am I done? No, now I have to divide by 2, right? I have to divide by 2 because I have that 2 over here. So I get my final result, x is equal to 7 pi over 8. There we go. 7 pi over 8. Okay? Now what I'm going to do is I'm going to go after trying to put these on a graph and then cut it into the equal intervals. I'm going to start a new page for this. Now notice something here. I'm going to choose right now to not put my y-axis in there. Okay? I mean, I could, but I'm not going to. I'm just going to put my 2 endpoints. Now, I have 2 endpoints. One of them was positive and one of them was negative, right? So make sure you get these in the correct order. The negative one should come first, right? Negative pi over 8. The other one was 7 pi over 8, which is somewhere over here. Notice I'm not putting any other information about the x-axis. Like, I'm not even labeling where 0 is. I'm not labeling where 2 pi is. I don't care about that. All I care about is where my function is doing something, right? So let's cut this interval in half. To do that, I'm going to have to add these 2 numbers and divide by 2. So we'll do that on the side here. If I take negative pi over 8, I add to it 7 pi over 8, and I divide by 2, what do I get? So add the 2 first. What's negative pi over 8 plus 7 pi over 8? 6 pi over 8. And divide that by 2, so you have 6 pi over 16, right? Which will reduce, but do you all agree that this is 6 pi over 16? Now reduce it because 2 goes into 6 and 2 goes into 16. So we get what? 3 pi over 8. Questions? So that's our middle one. And now we need to find one in between the negative pi over 8 and 3 pi over 8, which is here. So to do that one, we add these two, right? And then divide by 2. So maybe we can do this one mentally. I don't know. Can you do that one mentally? What's negative pi over 8 plus 3 pi over 8? 2 pi over 8. Divide by 2. 2 pi over 16. And that's just pi over 8, right? 2 pi over 16. So if you needed to, do it on the side, all right? But does anyone at least have a question as to, like, how in the hell I got that? Or, I mean, you understand what I'm doing with that? All right. Now I need to do the midpoint between these two right here. So I add them up. 3 pi over 8 plus 7 pi over 8 is 10 pi over 8 divided by 2 is 10 pi over 16, right? 10 pi over 16. And then reduce that. So what would you get? 5 pi over 8. Those are our 5 important points. And now I'd like to do what with those for step 4? Plug them in, right? Plug them into the original problem. So I'm going to plug these in. Y equals, geez, I don't even remember what it was. Was it negative 3? Hold on, I've got this blank page in here. There we go. Delete that. Yeah, negative 3 to, okay. So let's plug in the first point. Negative 3 sine, we have 2 times, the first one I'm going to plug in is negative pi over 8. And then I still had there what? Plus, what was my phase shift? Pi over 4. Trying to figure out what that's equal to. So what is 2 times negative pi over 8? This is negative 2 pi over 8, which really becomes negative pi over 4. So that's negative pi over 4 plus pi over 4. What's negative pi over 4 plus pi over 4? 0, right? So we get negative 3 times sine of 0. Now to figure out what sine of 0 is, we're now looking at the unit circle, right? We're looking at the y-coordinate this time instead of the x-coordinate. We're going to an angle of 0. What's the y-coordinate right there? 0. So the answer here is 0. So that means I can put a point at negative 8, 0. Which I kind of already knew that would happen because this is sine, right? We're pretty convinced that the endpoints are going to be zeros, right? Now, do you think you could repeat this process for each of the points? Yeah? I'm going to do one more. I'm going to do the pi over 8 because right now, what I can just tell you just by looking is that I already know with this sign that these 3 points are going to be 0. The question is whether or not it goes up and then back down, or if it goes down and then back up, because it can change. It can be different. So the pi over 8 is really the most interesting point for me. So let's plug in pi over 8. Negative 3 sine, let's see, 2 times, here comes pi over 8 in here, then plus pi over 4. That's negative 3 sine. Now we have positive pi over 4 plus another pi over 4. And what is pi over 4 plus pi over 4? Same denominator, right? So this is 2 pi over 4. What's 2 pi over 4? Pi over 2. So we have negative 3 sine of pi over 2. Okay, what's sine of pi over 2? So go to pi over 2 on the unit circle, which is 90 degrees. Look at the y-coordinate. What's the y-coordinate? 1, right? So this is negative 3 times 1, which is negative 3. You see, it does something a little different than what you may have thought. It's actually negative 3 when I'm at pi over 8. So I'm going to come in here and I'm going to put a point down here. That's negative 3. Now, how do I know that that's down 3? Well, I haven't put a y-axis in there, have I? So I need to, at some point, put a y-axis so everyone knows that that goes down 3. Now, where would my y-axis be? At 0, right? On the x-axis, so that would be right here, right in here. So I could just draw my x-axis or my y-axis in here. Now, again, you could have done that in the very beginning. It's really up to you. The reason I don't do it is because I really want you to focus on, we're just looking at a number line, we're trying to cut it in half and then cut it in half, and let's just get that all resolved first. The y-axis, how high things are, can all come in later. So I need to label this, what, negative 3 here, which means up here is positive 3. So do you see that our sine curve does something a little different than the normal? It doesn't go up and then back down. It goes down, then it's going to go back up. Why do you think it is that it did that? The negative in front, right? That negative 3, negatives in front of functions flip them over, right? The x-axis. So it's a reflection. So I do not need to actually go compute that 5/8 in there. I know this has to come up. If it's a sine curve, it's going to have to come back up. So now I connect. I go smile, smile, frown, frown. Now on your exam, which is going to be coming up at some point after we get through these trig functions, I'm only going to ask for 1 period on the exam, all right? Because the 2 periods, another period in each direction just takes too much time to go find those points. If you can do this, I'm happy, all right? Any questions on this? Okay, so what I'd like to do now is I'd like to do a problem similar to this, but now I'd like to add that vertical shift in, okay? The up and down shift. So for example 3, I'd like us to sketch y equals negative 3 sine 2x plus pi over 4 minus 2. So I've added this new element into it, right? That plus d is there. In the previous problem, it was not there, right? But does everyone agree that's the exact same problem? Yes? Now with the phase shift, right, the left and right shift, that phase shift is controlled by c, isn't it? That left-right shift is controlled by c. And since c is in my argument, that has an effect when I set the argument equal to 0 and 2 pi. If I change c, it changes the problem, doesn't it? But by changing d, that only moves your graph up and down, right? So the way that we're going to do this is to graph anything that has a vertical shift. We will ignore the shift until after we've graphed it. And then when we're done graphing it, we're just going to move the whole thing up or down. Understand? So I'm going to do this. I'm going to actually sketch y equals negative 3 sine 2x plus pi over 4, and that's it. First do that. So I am ignoring this shift. Ignore, all right? Ignore that for now, and go through the process of graphing this. Well, that's the problem we just did, right? That's the exact problem we just did. So I'm trying to save us some time here. So we know that this graph takes a little bit of time, but we would get this, we had negative pi over 8 here, we had pi over 8 here. What was the next one? Three pi over 8, then 5 pi over 8, and 7 pi over 8. And then when we graphed it, we got those points, didn't we? Yes? So I would say when you do this, be very careful that when you're plugging these points back in, plug them into this. Ignore that 2 out there. Was it a 2? Minus 2? Yeah. Ignore that, okay? Plug in those points, and here's what you would get. Now I'm going to do this, and when you do this, I would hope you do the same thing. Realizing you're going to move this later, don't come in here and draw this real dark. Do it like really light, or maybe do it dashed. You know that it started out at 0. It came down like this, right? It came back up like this, went up to 3, and came back down, right? That's what it did. And we know that these points, I'm going to put the points in there, but again, this is not our final picture, is it? No. But that's what it looks like. It just needs to be moved. Now, which way are we going to move it? Down 2. So every point comes down 2 from here. Does that make sense? So this point right here, this first point, used to be at 0. Now it's going to come down 1, 2. It's going to be here now. The point here used to be at negative 3. It's going to come down to, it's going to be at negative 5. This one used to be at 0. It's going to come down to, it's going to be at negative 2. This one used to be at 3. It's going to come down to and be at what? 1. And then the last one will be down to, it'll be at negative 2. So if you just drop all those points down too, and now come in with your dark graph, fill it all in, that's your final picture. So I'm going to come down to with this point, that's here. This one down to, what's that? Oh, did I put it at, oh yeah, sorry about that. Oops. Y'all see that? Where was that left point? That's why I hate the axis being in here. That point's supposed to be here, right? Okay, I just drew this little part of it wrong. It's got to come through. I'm glad you pointed that out. Thank you. Okay, this dotted right here actually starts here and dots down. Everyone got that fixed? That was my error. Okay, now move everything down 2. So 1, 2, that's here. I am extending my y-axis down to negative 5. So everything comes down 2 here, down 2 here, and then down 2 here. And then just come in and fill in, smile, frown. Read. What do you think? Think you could do that? So I'm going to label this here just so everyone's clear. This is actually our final product here. This is this minus 2. Just don't confuse it. It's not this one, right? That one right there is the blue dotted one. This one, the black one, is that. Okay. Any questions before I move on? Because now it's time to get into other trig functions. What I plan on doing is showing you how to graph cosecant and secant, and then hopefully at the end I can give you a problem that you can work on together in groups or something. All right. I don't know if we'll get to tangent and cotangent today. We'll just have to see. All right. So this is going to be, and then I believe it's the new section in the book, or new. Yeah, it's the new section 7.7. Yep, 7-7. It's graphs of cosecant, secant, tangent, cotangent. I'm just putting them by their three-letter abbreviation instead of writing out cosecant, secant, tangent, and cotangent. So we're going to start off with cosine, or cosecant, all right? So what is the definition of cosecant? If I write y equals cosecant x, remember that that really means the reciprocal of sine. So isn't that the same as this? Cosecant x is the same as 1 over sine x. Yes? Now, we have problems here. Because if I start asking you, what's the domain of this? With sine, the domain was everything, right? You could plug anything in, the sine curve goes in both directions forever. But with cosecant, we run into some problems, don't we? We could possibly have division by 0, couldn't we? When do we have division by 0? When do we have that happen? Whenever sine x is what? 0, right? So what we know for the domain is that sine of x can't be 0, right? The domain, we would have to say, look, the only way this function is defined is as long as sine of x is not 0. So tell me when that happens. Tell me when sine is 0. What's that? Every pi, every multiple of pi? So if we're asking ourselves this question, like, okay, if it can't be 0, then when is it 0? So I can throw those numbers out. Then I'm asking, when is that 0? So again, y-coordinate, right? Because you're on the unit circle, go to the y-coordinate, and you're asking yourself, when is the y-coordinate 0? So what place? Remember how we did this? When is the y-coordinate 0? It's going to happen looking at the y-coordinate, careful, because it's sine. The y-coordinate is 0 here and here, isn't it? That's where your y-coordinate is 0. How can we say all of those answers? K pi. All multiples of pi. So the way we did it, you go back and look at our last class, we said if you start out to the right, that's 0 degrees. To get to the next answer, you add how much? A pi. Then to get back to the other side, another pi, another pi, another pi. So we called that K pi, didn't we? Okay. So what we know then is for domain, the proper way to write this would be x cannot be any multiple of pi. See, we're saying when does this denominator become 0? Well, whenever x is a multiple of pi, sine of that will be 0, and that's not a good thing. So this function will not be defined at any multiple of pi. What do you think is going to happen whenever we get near those points? We're going to have asymptotes, just like in just like in college algebra with rational functions. Whenever denominator went to 0 and our numerator did not go to 0, then we had these weird asymptotes. We're going to have the same exact thing here. For now, though, we're just going to say domain you cannot have any multiple of pi. All right, what about the range? The range is a little more difficult. What was the range of a sine function? What was the range of sine? The range, what came out of sine? So it went up highest it ever got was 1, right? The lowest it ever got was -1. Now I'm talking about the basic sine function. I'm not changing its amplitude or shifting it. Just the basic sine function was stuck between -1 and 1, right? So now we're looking at the reciprocal of that. And it's a little more difficult to understand what's happening. So I'm just going to tell you what it is, and then we'll try and get our head around it once we start graphing it. The range of this is negative infinity to negative infinity to -1 union 1 to positive infinity. So what this is saying is that what comes out of it, sine had to be between -1 and 1, right? This one, what comes out of it has to be bigger than 1 and then actually less than -1. So it's kind of opposite of what the sine was doing, isn't it? Okay, so that's domain and range. Let's actually see how we're going to graph this, all right? This is a very interesting looking function. I'm trying to decide right now whether or not I want to really try and make you understand what's happening or if I want to just show you how to graph it, like without as much detail of the understanding of it. How many of you are doing Cal 1? Okay, that's enough that I think we need to kind of understand this. All right, let's go to a new page. Let's start with a graph, right? I'm going to come in here and I'm trying to graph this. Now let's first start out, remember I'm trying to graph y equals cosecant x, which is 1 over sine x. Let's start out with the places we know we can't have a function. Where can it not happen? We said k pi, right? So let me just go mark those. Here's pi. Here's 2 pi. I'll even go backwards, negative pi and negative 2 pi, just so I have a couple of them in there, zeros in there. Everyone agree that those are all multiples of pi? 0 pi, 2 pi, negative pi, negative 2 pi. Those are all multiples. So my graph can't be defined there. Since it can't be defined there, I'm going to draw asymptotes. This. All right, now let's just, we have an asymptote at 0, too. How do you draw a dotted line on top of a vertical line like this? My students in the past have always done like kind of little dashes that are almost diagonal a little bit so that you can really tell that there's an asymptote there. So can I plug 0 in and see what I get? No, right? So I need to plug something else in. So why don't we do this? Why don't we try something right in here? And something right here. So what's the number right between 0 and pi? Pi over 2, right? Then over here between pi and 2 pi is 3 pi over 2. You might know that just by thinking about the unit circle, or you could always, find halfway between two numbers, add them and take the average. Add them up and divide by 2. So let's try pi over 2. Let's actually plug into our function, what is cosecant of pi over 2? Well, that's 1 over sine of pi over 2. What is sine of pi over 2? 90 degrees, y coordinate, it's 1. So we get 1 here, don't we? 1 over 1 is 1. So I come over here. Here's 1 on my y-axis. I put a dot right here. Now here's where the people taking calculus, you got to really start to think about what's the way that functions behave. What is happening is I try and pick a point over here. Like let's say pi over 4. I could actually plug that in, couldn't I? Get sine of pi over 4 and figure it out? Yes? But let's think about it. On the unit circle, which I'll draw over here to the right side, if I go pi over 4 right here, sine is the y-coordinate, isn't it? Sine is the y-coordinate. We know it's root 2 over 2, don't we? But think about this. That y-coordinate, compare it to pi over 2. So remember, when we were at pi over 2, what was the answer? 1? That's because we were saying that this height right here was 1, yes? So if you take 1 and divide it by 1, you get 1, don't you? Okay. If I go over here to pi over 4, so now I'm getting a little bit smaller angle, then what happened to my y-coordinate? Did it get bigger or smaller? The y-coordinate. So as I came this way, the y-coordinate got smaller, right? What happens if I take a number like 1 and divide it by a smaller number? What happens to that fraction? It gets bigger, right? Think about it. 1 divided by 1 is 1. Yes? What's 1 divided by a half? 2, right? What's 1 divided by a third? 3. What's 1 divided by 1/10? 10, right? So as this number down here gets smaller, this fraction gets bigger, doesn't it? So what happens is as I move towards 0, as this angle gets smaller, the y-coordinate's getting smaller, which means that ratio is getting bigger. That's the key to like people going on in calculus, just understanding how things behave, how numbers affect each other. So as I'm moving this way, I plug in pi over 4. I could figure out the value, but it's more of a thought thing. These numbers should get bigger. I plug in another one here, it gets bigger. Another one here gets bigger, and it gets getting bigger and bigger and bigger and bigger. And there's an asymptote, so it seems natural that that asymptote shows you that your graph is going to just go up to infinity. And that's exactly what's happening. That makes sense? Like that. Now what happens if I go past pi over 2? So I get an angle. Now I'm going to stick between pi over 2 and pi. If I go this way, what's my y-coordinate? Is it getting bigger or smaller? My y-coordinate. It's still getting smaller, right? Same exact thing. So it's going to behave exactly the same going this way. As I get closer to pi over 2, the y-coordinate gets smaller, which means this ratio gets bigger, which means this becomes asymptotic, and it goes off to infinity. Do y'all follow that? What's going to be the difference, though, when we go on this side? If you're between pi and 2 pi on this circle, your y-coordinate is what? Negative, isn't it? It's negative. So let's plug in 3 pi over 2. That one I'll actually plug in. If I plug 3 pi over 2 in right here, what's sine of 3 pi over 2? So cosecant of 3 pi over 2 is 1 over sine of 3 pi over 2. What was it? Sine of 3 pi over 2? Negative 1. So isn't this negative 1 here? That gives you negative 1 when you plug 3 pi over 2 in. So I'm going to go to this graph, and I'm going to go down 1 and put a point. So when I'm going back to my unit circle here, when I'm pointing straight down, that red right there, when I'm pointing straight down, the y-coordinate is negative 1. 1 divided by negative 1 is negative 1. So that's why I'm here. But what would happen if I try and pick a number between pi and 3 pi over 2? So somewhere in here, as I move from 3 pi over 2 back towards pi, my y-coordinate's going to get smaller, right? But it's negative, isn't it? The y-coordinates over here are negative. They're negative. They're negative. What happens when you take 1 and divide it by a smaller and smaller negative number? You get a larger and larger negative number. Large negative numbers like negative 10, negative 100, negative 1,000, negative 10,000, negative a billion, right? Those are large negative numbers. So the behavior on this side of the graph, on this side, in between these two asymptotes, is that it's going to dive down towards negative infinity here. And then you can repeat the process on the other side. 3 pi over 2 to 2 pi, the y-coordinates are getting smaller and they're negative, so it's going to dive down like this. Understand? Now, because cosecant is just the reciprocal of sine, and sine was periodic, right? Sine just kept repeating itself. Then this should keep repeating itself. But that's the pattern of what it looks like. It's this thing, then another one, and then another one. Just keeps repeating. Goes in both directions forever. Yay or nay? Yes? Okay. Now, there's got to be a better way to graph it, right? Rather than just sit there and talk about, well, this is getting bigger and smaller and bigger ratio. So there is actually an easier way to do it. But I wanted to try and help you understand what was happening first. So let's just go back to our standard sine curve, right? That's sine x right there. And let me zoom out just a little bit. That's sine x. Let me bring in cosecant x, which is the reciprocal of sine. There it is, right? I told you it looked like these u's that repeat each other. Take a look at how it's connected to the sine. That u starts out at the top of sine, doesn't it? And that other u starts out at the bottom of this arc of sine, doesn't it? And where are my asymptotes? Everywhere where sine is 0, right? Wherever I see 0, I draw a vertical line. 0, I draw it here. You can't see it. 0 here, I draw it here. You see that? So the actual technique for graphing a cosecant function is to start off by first doing what? Graphing the sine of it. And then, once you graph the sine, you just come in and draw your vertical asymptotes and your u's and you're done. Y'all see that? So let's do an example. So your quiz problem. The first one was 4 sine 2x. This will be example 1 in this section. Let's sketch cosecant, 4 y equals, damn it, come on. 4 cosecant 2x. So what do you think we're going to do this? How are we going to do this? If I want to draw this cosecant function, probably should graph the sine of it first, right? Let's see, does changing the amplitude, oh wait, this thing is not, oh, I do have it connected. Yeah, look at how it changed. If I change the amplitude, what did it do to my cosecant? All it did is moved it up with it, right? Notice that these two curves are attached to each other, right? If I change the period, what happens? I just get more of them, right? More of those little asymptotes. The green one is the sine one. It's just stuck there. Just sine x, the original, yeah. Y'all see that? So all we have to do to graph this is be able to start by looking at sketching. What are we going to sketch? Y equals 4 sine 2x. We graph that, we're in business, right? So because you did that for your homework, right, and we did it last class, we already have this drawing in our notes. It was this right here, right? That was it right there. So I'm going to cheat, and I'm going to go grab that real quick, and I'm going to throw it down on the piece of paper. I'm going to take out those extra periods we had in there. Take out some of those dots. So what we would do here is we would make sure we have all the detail in the picture. We still would have to find the period. We'd have to find those points. We'd have to plug them in. We'd have to get the general picture. But instead of drawing that sine curve like that, I would recommend you come in and draw it dashed. Why? Because that's not our final answer, right? Our final answer is going to be the cosecant. So draw your sine curve. Now let's begin to draw the cosecant. How do we draw cosecant? Well, we first start out at the x-intercepts of the sine function. Anywhere we see an x-intercept, we do what? Draw a vertical asymptote. So I'm going to go to each of these, draw a vertical. Wherever my sine function was 0, draw a vertical. Can you all see my vertical there? I have 3 vertical asymptotes. And now come in and draw the cosecant function. So it will always have these U-looking things, right? I go to the peak of the sine, I draw a U up there. I go to the peak down here, I draw a U downward. So I'm going to go like this, and then down here, same thing. Do you see now, do you see why we said that the cosecant range was between negative infinity to negative 1 and then from 1 to infinity? You see that? Your cosecant never does anything in there. The sine function actually keeps it out of that area, and then it just goes below it and above it. Yes? So on your test, do you think that I'm going to ask you to graph a sine function? Probably not. I'm going to ask you to draw a cosecant function. Because if you can only draw a cosecant function if you can draw a sine function. So you probably won't ever see a sine problem on the test. Now, how do you think it works for cosecant? Cosecant's the reciprocal of cosine, isn't it? Cosecant x is 1 over cosine x? What did I just say? It's Monday, man. It's Monday, 9 a.m. This is why I don't sign up for Monday 9 a.m.s ever. I always teach at 11 o'clock and on, because I don't wake up till about 10:45. Mentally. Okay, start over. Cosecant x is this. So how do you think we're going to draw secant x? We look at cosine, right? Because secant is a reciprocal of cosine. Same exact story. You draw the cosine. Wherever the cosine hits the x-axis, you draw vertical asymptotes, and then you just draw your little u's, and you're done. So it's very much the same thing. So let me take cosecant and sine out of here. Here's your cosine function, right? That green one is the regular cosine function. I'll put this back to initial settings. Here's cosine, all right? Let's zoom out a little bit. There's your cosine curve. Now here comes secant. It's reciprocal. So everywhere where cosine was 0, I draw a vertical asymptote, and then I draw the little u parts. Yes? All right, so we'll do one of these because there's a slight little modification we have to make. You'll see. And then I think we might be able to talk about tangent and cotangent. It's good. Okay, so example 3. Sketch. We'll keep this one pretty basic, but I'm going to throw a little bit of a curve at you. And I'm going to move kind of quick because we need to start moving quick. All right, oh, I forgot to put secant. I put cosine. Why did I do that? Because it's before 11 o'clock. That's why. That's my excuse for everything now. So to graph this, I'm going to say y equals negative cosine 4x. I need to be able to graph that. So to do this, I look at it, what's my amplitude? Remember, the amplitude is the absolute value of the number out in front. So the amplitude is -1 absolute value, so it's just 1. So this is like a normal cosine, but I've got a little bit of a change happening. What does that 4 affect? Is it a phase shift? Is it a vertical? What is it? Period, right? It's a change in the period. So I'm going to find my 2 endpoints. So I take this argument, I set it equal to 0 and to 2 pi, right? I'm not showing this work. Setting it equal to 0, I get 0. Setting it equal to 2 pi, I get pi over 2. Not showing that work. I'm skipping a lot of the work just because, again, time. I'm trusting that you could follow the method from earlier in the class and graph this on your own. Halfway between 0 and pi over 2 is pi over 4. Halfway between pi over 4 and 0 is pi over 8. And then halfway over here would be 3 pi over 8. However you do that, you need to be able to get those numbers. I will bring in my y-axis. I'm hesitant to do so, but I will. My amplitude was 1. So it's going to be like 1 here, -1 here. And I would take these points, right? 1, 2, 3, 4, 5 points. I would plug them into the original cosine curve, right? And I would get my cosine function. And it's actually flipped over because of the negative. So if you did that, you would get something like this. You would start here, go up here, down here, and then end back over here. So I would do like smile, frown, frown, smile. That's what it would look like. I hope you realize that there's like, maybe 10 minutes of work here, that I didn't show. It depends on you, right? Like how comfortable you are with all of this. But I'm not expecting that you would just be able to slap the negative cosine 4x up there like that. But I am expecting you could get to it eventually. So we do this, right? And now we're ready to actually graph the secant. So to do that, we go to the cosine curve. Anywhere it hits the x-axis, we put a vertical asymptote. So I have one here. And I have one here. Those are the only 2 x-intercepts I have, don't I? Right? That's it. This is why I'm showing this to you. This is where things get a little weird. Because to graph the secant, I need to draw a U that goes between the vertical, right? And it's going to start at that peak. So I've got one of the U's. I'll put it in black. It starts here, and it goes like this. But what's wrong with the other U's? I only have half of it, right? Like, look, here's the point, right? There's another vertical asymptote over here somewhere, isn't there? And then over here, this is half of it, and then there's another vertical asymptote somewhere over here. So in order to actually fill it out completely, I would actually need to continue this period back up to the x-intercept, or continue this one back to the x-intercept. Yes? Do you all follow that? But what I'm okay with on a test is you understanding that we're just looking at this one part, and you drawing just the half here and this half like this. As long as you're okay, as long as you understand that part of it, that there is more to the picture, you could continue it and have the other part come down, I'm okay with that. Is that fair? Okay. That's it. So to graph cosecant and secant, you just have to be able to graph sine and cosine respectively. Draw the asymptotes, draw your U's. All right. Next idea. How about example? I'm going to make this an example, but I'm actually now talking about tangent. Example 4. Let's try to graph y equals tangent x. Well, tangent by definition is the sine divided by cosine, sine over cosine. So if I look at that, I'm going to have domain problems again, right? I'm going to have division by 0 whenever what? Whenever cosine is 0, right? When I'm talking domain here, cosine x cannot be 0. So go to your unit circle. Cosine is the x-coordinate. When does that happen? When is the x-coordinate 0? The x-coordinate is 0 at pi over 2 and 3 pi over 2, right? So I should have asymptotes there, shouldn't I? Okay, so let me just start with that. I'm just trying to paste this thing together real quick. It's very much motivated the same way that the cosecant and secant were. I know that at pi over 2, so I'm kind of guessing at this. If this is pi over 2, this would be pi, and then this would be 3 pi over 2. I know I'm going to have asymptotes here. Y'all agree with that? In fact, I actually could have gone on the other side of the y-axis, and I could have put this in, couldn't I? Negative pi over 2. Because to get to this point on top, I can rotate by pi over 2. To get to the point on the bottom, I could have gone clockwise direction, which is a negative angle. I could have gone negative pi over 2, and that would have given me this. Y'all okay with that? All right, so let's see what happens here. I know I have asymptotes here, but what's happening in between? So why don't we go right in the middle? Why don't we just see what's happening right in the middle of these? So how about right here? What angle is right there? 0. What's tangent of 0? So tangent is your y-coordinate divided by your x-coordinate. Remember? If you go to your unit circle, tangent is the ratio of the y-coordinate divided by x. So if you go to your unit circle, go here. This is the point 1, 0. If I say what's tangent of 0, you go 0 degrees. You take your y and divide it by your x. 0 divided by x, or 0 divided by 1 would be 0. So I should have, my graph should actually be at 0 here. Let's see if we can follow this logic now, again. What if I try and make my angle get closer to pi over 2? What's going to happen? So notice my angle here is getting closer to pi over 2, so what's happening pi over 2 over here? So tell me, is it positive or negative? Positive, right? Tangent is positive in the first quadrant, isn't it? So I know it's a positive number, so I know it's up, but it's the y divided by the x, right? So take a look at this. Initially, which one's bigger over here? If I'm at a point, let's say right here, which coordinate is bigger, the y or the x? The x is bigger, right? So you have a small number. If you're right in here, right, this is big, this is small. So tangent, you take the small, that's the y-coordinate, you divide it by the big. If you take a small number and divide it by a big number, what is it? So like take 1, which is kind of small, and divide it by a big number like 100. It's small, right? But what happens as I move around is it changes, right? This number right here, now the small one is the x-coordinate and the big one is the y-coordinate. And then when you do that ratio, take a big number and divide it by a small number, what happens? So take 100 and divide that by 1. That's 100, right? Take 1,000 and divide it by an even smaller number, like 1/10, and then that becomes like 10,000. So what's happening is as I'm moving up like that, my ratios are getting huge and they're positive. So my graph is asymptotic. I mean, you can kind of tell that it's asymptotic because you have a freaking asymptote there, right? I mean, you know it's going to do that, but it's a question was, does it go up or down? But I like people to understand like the number sense part of it. It's the ratio that's changing as you're moving closer, smaller and bigger. That's all what calculus is about. It's about what's happening as we get close to things, get closer and closer without actually getting there, just like what's happening, the behavior of things. So understanding it is, I think, more valuable than just being like, oh, when you see a tangent, you just go like that and just draw it up. Now, what happens on the other side? So between the angle 0 and negative pi over 2, aren't you rotating down this way now? So we have the same sort of pattern. Initially, this point right here has a big x-coordinate and a negative small y-coordinate, right? Sorry, this is very tiny over there, but I'm trying to squeeze it in. It's negative small, right? Because your y-coordinate's negative, and then your x-coordinate is big. As I move over, though, what happens is that your x-coordinate is small, right? And your y-coordinate is a negative big number. And if I take a negative big number and divide it by a very small positive number, I get a very big negative number. So your asymptote this time goes down like that. And this right here is what we call a single period of tangent. From here on out, it repeats itself. So if you go back and you look here, halfway it's going to go down. And then it's just going to do the same thing behind this and over here. So that's your behavior of the tangent. So the period of tangent, how wide is the period of tangent? What's the distance between these two? Pi, right? It's pi over 2 in each direction. So the total period is pi. What's the period of sine? 2 pi. Cosine? 2 pi. Secant? 2 pi. Cosecant? 2 pi. It's not until you get to tangent where the pi is different, or the period is different. Tangent's going to repeat itself every pi instead of every 2 pi. If you don't believe it, just go in here, plug in some values over here, plug in some values over here, go to the circle, just make the same argument, you'll turn out to have the same thing happen. Okay. Yes? You could just plug in points. So like just go around your circle, take your y-coordinate divided by your x-coordinate, get that number. Do the same thing for all the points that you know on the unit circle, and you'll convince yourself that what's happening is as you move this way, they're getting bigger. And then you just have to say, okay, well, it looks like it's going to go up to infinity. The asymptote has to be there, though. So are you okay with that idea? It's going to have to go up or down? All right, so what about cotangent? Cotangent. For y equals cotangent x, cotangent by definition is cosine over sine, isn't it? Instead of sine over cosine? So your asymptotes are actually going to occur at a different place, aren't they? Wherever sine is 0 instead of cosine? And where is sine 0? Where is sine 0? Here and here, right? 0 and pi, so k pi again. That's where we're going to have problems. So I'm going to come over here to a graph. 0, let's say at pi. I'll go negative pi, 2 pi. I know that at every one of those, I should have asymptotes. Understand that part of it? All right, let's look at the period. Looks like it's going to be pi again, just like the tangent was, from 0 to pi, and then from pi to 2 pi. It looks like it's going to repeat itself possibly. Let's try and figure out what's happening right in here. Let's pick a value right in the middle. So what's that value? Pi over 2? Okay, let's plug it in. What is cotangent of pi over 2? So what do you do to figure this out? You do cosine of pi over 2 over sine of pi over 2? What's cosine of pi over 2? What's sine of pi over 2? When I say cosine of pi over 2, you're going to your unit circle, you're going to the x-coordinate, you get 0, right? What is sine of pi over 2? You go to the unit circle, you go to your y-coordinate, pi over 2, and you get 1. And so you get 0. So we have a 0 here, right? Well, it's looking very promising. That's going to look very much like tangent, right? Maybe it's going to drop down and go up. Okay, well, I'll try something a little different than the big, small thing this time, okay? I know that when I draw this, it's either going to go up or down here, and then on this way, it's going to go, up or down because of the asymptote. Do you agree with that, at least? Okay, so let's try something in here like pi over 4. Tell me if you plug pi over 4 in, here's pi over 4 on my circle. What is cotangent to pi over 4? So that's cosine of pi over 4 divided by sine of pi over 4. What's that? It's 1. Good. Because you're taking the x-coordinate divided by the y-coordinate. So you get 1. So that means that at pi over 4, I'm up here at 1. Is that good enough to tell you that if I kept doing this, since these are positive, my asymptote's going to go up? Yeah, okay. Forget the big, small thing. It's just, that's the only thing it can do, really. And then if I plug in something like over here, what's a good angle I could plug in that's right here? 3 pi over 4? That'd be this one. What's cotangent over there? Is it positive or negative? It's negative, right? Cotangent's negative here because you're in the second quadrant. Cotangent's reciprocal of tangent, so whatever tangent is over there, it's also. So it's negative. That means that you could have a point down here, and so that kind of helps you see that your asymptote's going to do this. And that's it. It just keeps repeating itself. Halfway through, goes up, goes down. Now, I'm not going to have you graph anything more complicated than just tangent and cotangent. That's it. Like, we're not going to move it around and move it up and down. You just need to understand what the basic tangent and cotangent functions look like. Tangent, I'll bring that back up. Tangent looks like this. Tangent has a period of what? This is tangent. Period of pi. One period, the first period occurs between negative pi over 2 and pi over 2, right? And then it goes down on the left, up on the right, it goes through 0. Cotangent, and I'll leave tangent up there for a second. Cotangent looks the same, but it looks flipped over, right? But there's also a difference. The period has been moved. The period's still pi, but there's like a little phase shift. Instead of going between negative pi over 2 and pi over 2, the first period of cotangent is between what? 0 and pi. See the difference? Yes? So as a student of pre-calculus, if someone were to ask you to do a quick sketch of tangent, here's what you do. Tangent, right? You go, tangent. I know that tangent goes between negative pi over 2, pi over 2, because I've memorized that, and I know there's an asymptote. I know it goes through right through 0. I know it goes down and that goes up. And that's what a tangent function looks like right there. It should be a quick sketch. If it's cotangent, then you have to say, all right, I know cotangent is between 0 and pi, not negative pi over 2 and pi. And pi over 2. It's 0 and pi. Those are where my asymptotes are. And right through the middle, I got 0. And it's the opposite. It goes up and then it goes down. There's your cotangent. Then you could just repeat those in each direction if you needed to. We good? Okay. All right, I think we've covered a good amount of material today. So let me give you something to look at. I'm not going to overload you with homework, what I'm going to do is give you a few problems that are going to require you to take some time to graph, okay? This is going to come off of page 592. Now, don't freak out that this is out of 7-8. This is out of 7-8 in the book. We didn't really talk about 7-8. It's 7-8 is where they did all the phase shifting and all that. I kind of like tried to throw it all together into one idea instead of breaking it up in different sections. So problems 3. Just want to make sure there's no surprises here. That's a good one. Okay, problems 3 and 5 and 7. Those are all pretty much fair game. I mean, there's nothing special about those. But once you get to 9, 11, I'll throw 13 in there. Things will be a little bit different. And you're just gonna have to see what I mean by doing it. I mean, it's the same setup. All of those problems are graphing sine and cosines. All right? Because I think if you can graph sine and cosine, all this secant, cosecant stuff is just going to be easy after that, right? Just drawing your verticals and drawing your little u's. So work on those 6 problems as your homework. Don't follow the directions in the book, okay? The book are like find amplitude, period, phase shift, graph, show 2 periods. All I want you to do for each of those is what we did in class, all right? Give me 1 period, nice and labeled, x-axis, all the points. Would you all like that as a quiz grade? Does that sound like a good idea? I don't see you till Monday, so I mean, you have a whole week to graph 6 trig functions. Yes? We'll turn it in on Monday, all right? Oh, you want bonus? You like bonus? Everyone loves bonus, right? For each of the 6, for each of these 6, draw what their reciprocals would be. So like on number 3, I'll tell you, like number 3 is y equals 4 sine of 2x minus pi, right? For bonus, on a separate page, or no, you could do it on the graph, so I won't even make you have to redraw the whole thing. But on your same graph, if you actually graph with it, y equals 4 what? What do you think? Cosecant 2x minus pi. If you graph that with it together, then I'll give you a little bonus, all right? And do that for each of the problems. So if it's a cosine problem, you'll graph the secant with it. Yes? Understand? Okay. It's rare that I say this, but have a good weekend. If I don't see you before. Yes.